Okay, 17.3 is all about changes of state and changes of temperature. Okay, so we're going to start talking about a couple of reactions and think about their delta H's. Remember, delta H is the change in enthalpy or the change in energy associated with those reactants becoming those products. So this first slide is about why it's important to give states of matter. So if we look at these two reactions, take a second and try to identify the difference between them. Okay, you may have noticed that the products are the same for both, but in this one we have liquid water breaking up, and in this one we have gaseous water breaking up. Okay, so the first question then is, regardless of how these delta H's compare, would you expect them to be positive or negative? So I want you to think about when you decompose water, does it release energy or does it require energy? And a good question to ask yourself is, do you know that answer for the reverse reaction? So when hydrogen and oxygen get together, I think you may remember that it releases tons of energy when hydrogen reacts with oxygen, right? We did that with the balloons. So if that releases energy to form water, then it must require energy to break up water, which means that it's endothermic, which means that these are positive. Energy is required, energy will be a reactant. Okay, so then which one would be more positive? So thinking about how one is liquid water becoming gaseous hydrogen and oxygen, one is gaseous water becoming gaseous hydrogen and oxygen. Okay, so the only difference between these is that this reaction up here not only has to break apart the water, it also has to vaporize the water. Whereas this one is already vaporized and it only has to break it apart. So the step of turning the liquid water into gaseous water requires extra energy. Therefore, this one will be more positive and this one will be positive, but less strongly positive. Okay, so these are the actual numerical values here, 285 versus 241 kilojoules per mole reaction. Remember, this unit means that for every 1 mole of H2O broken apart, and for every 1 mole of H2 produced, and for every half mole of O2 produced, 285.8 kilojoules of heat are required, right? Reactant. Okay, so this is a question that might take a second to process. The vaporization of 1 mole of liquid water to water vapor at 25 degrees Celsius requires how much heat? Okay, so what we notice in these two reactions is that both of them have this happening, right? Gaseous water becomes gaseous elements. But this one has the additional step of the liquid becoming gas and then becoming both products. Okay, so the difference between them is that the top one includes the vaporization and the bottom one doesn't. So we can actually use that information to parse out how much of the top one's delta H is from vaporization compared to the bottom one. So let's write out our reaction here to see what this is even talking about. The vaporization of 1 mole of liquid water to water vapor. Vaporization, liquid water, 1 mole to water vapor. This is the reaction that we're looking at, okay? And again, this is the reaction that the first reaction up here includes, that the second one does not, okay? So the difference between their H's will tell us how much of the delta H is because of this step. So when we do that calculation, we get 44.0 kilojoules per mole, and that is the amount of heat required for this step. Okay, just one more time to repeat that. It's like the first reaction includes 2 steps and the second reaction includes only the second step. So to find the delta H for the first step, you just find the difference. Because it's included in this one, it's not included in this one. Okay, so we're going to talk about what heat can do when there's no chemical reaction. So we're ignoring, like the one we just did above, where something becomes something else. We're ignoring that. We're only talking about these two other things that heat can do. So what can heat do when it's gained by a substance? It can either change temp or it can change state of matter. Okay, so let's think about this example we're going to talk about a lot here. Let's say that you have, we're going to call this temp over here, and we're going to call it temp in degrees Celsius. That's really good. And we're going to call our bottom axis is going to be heat gained. Okay, so we're going to see how temperature changes as a function of how much heat is gained by a substance. We're going to talk about water, because water is what we always talk about. What would be a unit of heat? Kilojoules is fine. The actual units don't really matter because we're not doing this quantitatively, we're more doing it qualitatively, but we can still write it. Well, maybe we'll do it a little quantitatively. Okay, so let's say that you start at negative 50 degrees Celsius. Oops. Okay, and you add heat to a bunch of ice. What's going to happen to it? Is it going to change temperature or going to change state? Okay, it's going to change temperature. So as you add heat, its temperature will go up, right? That's just the relationship between those two things. So we're going to draw it like that. Okay, and then it's going to suddenly stop. It's going to suddenly stop changing temperature. I'm going to make that a little shorter. So why would it suddenly stop changing temperature? What point has it gotten to? 0. Okay, so now instead of increasing in temperature, you know that when ice gets up to its melting point, it will just sit at that temperature and melt for a while. So even though we continue to add heat, there's no temperature change because it's just melting. So we have this happening, but not this, okay? So eventually it all becomes liquid water. So maybe we should just point that out. Okay, so this is ice. Okay, at this point right here, we have ice at 0 degrees. And at this point, before we transition to the next thing, we have water at 0 degrees. Okay, so that whole process there, that line, just represented melting. Okay, so then once you have water at 0 degrees and you keep adding heat, obviously it will get warmer then, right? So we're going to show this big long stretch where the water is getting warmer. Okay, and what point did we stop at here? Water, it's still water at what temperature? 100. Because now, instead of continuing to get warmer, it's going to do a phase change. Okay, so let's draw that phase change. Constant temperature. Like when I had that water boiling for that specific heat of a metal lab, it was at 100 degrees. The whole time it was boiling. I could have checked it again 5 minutes later and it still would have been 100 degrees. So boiling water stays at 100 degrees until all the water is gone. And then what you have left is water vapor, right? At 100 degrees. So this whole thing is just a phase change. We'll call this, I can do it in red, I guess. This is boiling. This is melting. Okay, these long stretches here, this is heating water. Okay, this here is heating ice. Okay, and we have one last step here. We're going to do, once you get to water, it's all boiled off, and you keep adding heat, and that'll just go up indefinitely. Then you have heating water vapor, which is just steam. Gaseous water. Okay, so this is what a heating curve looks like. There's a lot of words, but the basic shape, up, over, up, over, up, is what all substances will look like in terms of their heating curve. Because for every phase change, the temperature becomes constant, and then within a particular state of matter, added heat will change the temperature and not change the phase. Okay. 'Cause, 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 just had a moment of fear that the camera's not on, or that the microphone isn't on. Okay. All right, thank goodness. Okay, so here's a better version of it that is mathematically accurate. Okay, so I would take a second, ask yourself what's happening at all these different stages. So the first thing is, what are 1, 2, 3, 4, and 5? And what do you have at all of these points? Okay, and then you can check your answer with the previous slide. Okay, so in this conversation, we introduced a couple new types of delta H. Okay, remember delta H is the heat of reaction, but you can also have specific delta H's like heat of combustion, heat of solution. Now we have heat of fusion, heat of solidification. So these are specific delta H's that refer to specific temperatures, or sorry, specific reactions. We actually introduced one of them up here. Where are you? Here we showed liquid water becoming gaseous water. So this was technically heat of vaporization. We just didn't write that. That says VAP for vaporization. Okay, so 4 new kinds. Heat of fusion is when a solid becomes a liquid. So fusion, I'm not sure why it says that. It's basically, we've looked this up before, the etymology of this, and kind of registered and then disappeared. Okay, so melting. So this is the opposite. Solidification would be when a liquid becomes a solid. That's a little more obvious. Delta H VAP is the energy change associated with a liquid becoming a vapor, and delta H condensation is the opposite, the heat change associated with a vapor becoming a liquid. Okay, so let's, is there any more about that? Yeah, okay. Okay, so we'll get there. Yeah, okay. That's all I'll say about that for now. Okay, so let's look at this curve one more time and talk about the magnitude of a couple different things. Okay, so the first question here is asking about the magnitude of the specific heat capacity of ice and water vapor. Okay, so that's this value. The specific heat capacity relates to how much heat needs to be added to either the ice state of matter or the gas water vapor state of matter in order to change its temperature. Okay, so which of those would you think would have a greater magnitude? Okay, trick question. They're similar. Okay, and how do we know that? Because they change temperature at about the same rate, right? So you can, how do you tell the rate of the change of temperature on this graph? The slope for that particular section represents the rate of the change of temperature, okay? And because they have similar slopes, oops, they have similar C values, okay? I've actually never really thought about this before, but yeah, you know Q equals MCAT. Slope is rise over run. The rise is delta T. The run is Q. Yeah. Anyways, is it like this? I shouldn't be doing this for the first time right now. Anyways, I guess what you can see is that there's a direct relationship between the slope and the value of C, but you would also see that a smaller value of C would lead to a higher slope, which does make sense actually. We'll get to that later though. Okay. Yeah, we'll come back to this. This will come up again. Okay, let's think about this. So, based on this graph, what's has a larger magnitude, the heat of fusion or the heat of vaporization? Okay, heat of vaporization. Okay, the reason being that in order to melt this substance, we can use the blue, only this much heat was required, right? Because you can't really tell here, but it says heat applied. Whereas in order to boil it, all of this heat was required. Okay, so we can see from the length of the phase change section. How much heat was required for that phase change, which gives you a sense of how much of the value of delta H for that substance. Okay, the point that I was going to make up here that I forgot to make was, if you think about temperature versus heat, think about something with a well, never mind, I'll tell you in just a second. Okay, so this is our last question on this. What is higher, the specific heat of water or the specific heat of ice? Okay, water. Okay, why? So specific heat is a measure of how much heat is required to cause a specific temperature change. So I'm going to zoom in on this, okay? So let's say that we're looking to cause this temperature change, okay? I'm going to try to make it the same for the ice section and the water section. Okay, so we're changing the temperature this much, okay? So let's look at how much heat would be required to do that. Okay, so if we go over to water, we're gonna kind of project this over. Okay, and we're gonna do the same for the ice because we wanna see how much, and this is again just related to slope for those of you that like to think of it that way, how much heat is required for this change, okay? So we can see that in order to cause, let's parallel, okay. In order to cause that temperature change for water, this much heat is required, right? In order to cause the same temperature change for ice, I even did that in kind of the wrong spot, but you can tell that less energy is required. Do you guys see that? So things that change temperature more quickly indicate, and quickly is assuming constant heat, right? So quickly, maybe I should say things that change temperature with less heat indicate lower specific heat capacity. Okay? Okay. I could have done a bigger temperature range and it might have been more clear, but I think it's still clear. All right. Ugh, morning voice. No road noise, but morning voice. Okay. You can even tell what time it is. That's funny. Or can you? You probably can. All right. Then looking at these values then, is delta H positive for endothermic or exothermic? So remember, delta H is positive for endothermic, for things that require heat. Okay, in our little graph there, if we're showing the reaction pathway, when we go up and form higher energy products, this is delta H, and it's positive when the final is greater than the initial. Okay? So which of these require heat? Which of these has a positive delta H? So fusion, melting, requires heat, positive delta H. Okay, we're going to call it endothermic. Condensation, when something solidifies, loses heat. Right, like water vapor hits a cold soda can, heat from the water vapor goes into the soda can, and the water vapor gets colder and condenses. Exothermic. Okay, solidification, similar to condensation. Vaporization, in contrast, you have to heat things up, add heat to get them to vaporize. Okay. So what you can also see here is that if, I'm going to write this reaction out again, liquid water becomes water vapor. Okay, and delta H for this was 44, wasn't it? I know it's positive, okay, because heat is required. So if we were to include it in the equation, which is another legitimate way of showing it, we would write it as a reactant, okay? And if we were going to be more specific over here about what delta H we were looking at, we would say this is the delta H of vaporization. Okay, you can also write this reaction the other way around, can't you? Where gas becomes liquid. That is condensation. And you see this nice relationship where if you write the reaction in the opposite direction, the magnitude of delta H will stay the same, but because it goes from being a reactant to a product or a product to a reactant, the sign of it will change. So that's just highlighting this relationship here. That delta H vap and delta H condensation will have the same magnitude, opposite sign, because it represents the same process in opposite directions, which is opposite processes. But anyways, you know what I mean. Okay, and the units are usually kilojoules per mole. Okay, we're going to do one more slide here and stop. How far are we? This is getting long, huh? Yeah, okay. Okay, 2 equations. If there's a change in temperature, what's our equation? MCAT, right? Change in temperature. Okay, we use specific heat. Okay, if there's not a change in temperature, there's a phase change. Okay, and the things we were just talking about that relate to the amount of energy associated with the phase change are delta H's. And the units of delta H's are kilojoules per mole. So if you're trying to just isolate heat, you need to take out the mole part, right? So delta H has units of kilojoules per mole. So what would we multiply it by to just get Q, which is just heat? We'd multiply by N. Okay, when you multiply kilojoules per mole by mole, you get kilojoules. It's good to remember, though, that this is going to be in joules and this is going to be in kilojoules, so that's going to come up later. All right, we're stopping there.